Welcome back to the next video, everybody. Today we're going to be looking at some more basic elliptic curve theory, although this theory will be somewhat more advanced than the last video I made on elliptic curve theory. The motivation for this video is very simply, there's a lot of key results about elliptic curves that were needed in the proof of the fivefold theorem from the previous video. And while I do have a separate chapter on the fivefold theorem and its proof, I thought it would be good to look at some of the results on elliptic curves needed now, because a lot of the results that I've selected are all just kind of fundamental pillars of the field of study of the arithmetic of elliptic curves, and you should know about these results. They're used at various points throughout the proof of Fermat's last theorem, so there's no reason not to know them. Okay, so first up is the Hasse bound. Let's let P be a prime. Let's let Q equals P to the K for some natural number K. Let's let E over FQ be an elliptic curve. Then AQE, an absolute value, which is the absolute value of Q plus 1 minus the number of FQ points on E, is at most 2 root Q. So what this is saying is that within a reasonable margin of error, the number of FQ points on E is Q plus 1. Okay, so you can see Silverman 1, page 138 for a proof of this. So why do I bring this result up? Well, if I give you an elliptic curve E over FQ, let's let phi from E to E be the Q power Frobenius map that sends a point xy to x to the q, y to the q. As you're proving the Hasse bound, you find out that the trace of Frobenius, which is phi plus phi hat, where phi hat is the so-called dual isogeny to phi, you can see Silverman 1 for the theory of dual isogenies, is the same as multiplication by AQE. And from this, it's pretty easy to conclude that FQ isogenous elliptic curves over FQ have the same number of FQ points. And for a proof of this, you can see Cornell, Silverman, Stevens modular forms in Fermat's last theorem, page 23. All right. And the reason this is called trace of Frobenius has to do with the Galois representations attached to the elliptic curve. Okay. So the nutshell here is FQ isogenous elliptic curves over FQ have the same number of FQ points. So keep that in mind. It turns out the converse is true, although we won't need it. This follows from Tate's isogeny theorem. You can see Silverman 1, chapter 3 for the statement of the theorem. However, you need to see some other reference if you want to look at the proof. So for example, I think this is Papikian. I'm not sure how you say that, but Honda-Tate theorem for elliptic curves, especially corollary 3.6, gives you a proof of Tate's isogeny theorem and also a proof of the converse that I claimed is true. So what do I mean by the converse? I mean, so the statement here was, give me two FQ isogenous elliptic curves over FQ, then those two elliptic curves have the same number of FQ points on them. But the converse is also true. If two elliptic curves over FQ have the same number of FQ points, they must be FQ isogenous. Okay, so that follows from Tate's isogeny theorem. By the way, just if you go read this reference here, this Honda-Tate theorem reference, the equivalence 3 if and only if 4 in that paper requires Brouwer and Nesbitt, right? I would also recommend looking up Edixhoven, Gear, Moonins, abelian varieties and looking at chapter 16 to see more details about this kind of thing. And then you can see Diamond and Sherman to fill in basic missing information about Galois representations attached to elliptic curves if you need that information while doing these studies. But again, I'm not going to say too much more about this because we don't actually need this converse. Okay, so let's let K over QP be a finite extension which is complete with respect to some discrete valuation V. And let's let R be its ring of integers, and let's let lowercase k be the residue field of R, and let's let sigma be a set on which the absolute Galois group of K, G sub K, acts. We'll say sigma is unramified at V if the action of the inertia group IV on sigma is trivial. That's always what unramified means when we're talking about that term. Well, not always, but that's usually what it means. Okay, so inertia acts trivially. So I bring up that definition just so I can state the following crucial theorem about elliptic curves, and so then all the terminology will make sense to you. So theorem, Neuron-Shafarevich, let's let big K and little k be as above, and let's let E over big K be an elliptic curve. The following are equivalent. E has good reduction at the place V. That is, the reduction of E tilde, the reduction E tilde of E mod the maximum ideal M of R is non-singular. If you like, I mean, what model of E am I reducing to produce E tilde? You could take a Neuron model, for example. You could also take probably just a local minimal model at V, but okay, so take some special model of E, reduce that mod M. That's what I mean by the reduction E tilde of E mod V. Okay, 2, the M torsion of E is unramified at V for infinitely many M bigger than or equal to 1 co-prime to the characteristic of little k. So remember, the M torsion of E is certainly a GK module, so this makes sense, right? 3, The M torsion of E is unramified at V for all M at least one coprime to the characteristic of K. So that's a bit of a surprise. And then 4, the L-adic Tate module of E, so that's the inverse limit over N of the L to the N torsion of E, is unramified at V for some, or equivalently actually all, primes L which aren't equal to the characteristic of K. All right. So this is a bit, wordy, and it's stated very locally. So let's see one example of how you might use this. All right. So here's the corollary that I'm mainly interested in today's video. I would say this is the big result of the video, well, half of the big result of the video. Okay. Let's let E over Q and E prime over Q be Q isogenous elliptic curves. Then for all primes P, APE equals APE prime, and hence the L function of E is the same as the L function of E prime. In fact, this remains true for elliptic curves over number fields, but we're just going to look at the proof over Q. So Q isogenous elliptic curves over Q have the same L function. Okay, so here's the proof. Consider a Q isogeny F from E to E prime. We know Q isogenous elliptic curves have isomorphic L-adic Tate modules if L is a prime not lying below V, such that L does not divide N, where N is the degree of the map F. Okay. So why is that true? Well, if you compose F with its so-called dual isogeny from E prime to E going the other way, you get a map from E to E prime coinciding with multiplication by N. Okay, now, so that's just basic dual isogeny theory. You can find that in Silverman 1. Now, multiplication by N on E induces an automorphism, which we'll also call multiplication by N on the L-adic Tate module of E. Okay, that's not hard to see at all. Now, if you compose in the other order, this is again a basic property of dual isogenies, you get an automorphism, which I'll also call multiplication by N on the L-adic Tate module of E prime. Now look, both of these compositions on the level of Tate modules are multiplication by N. Multiplication by N, because it doesn't divide N, is an automorphism, okay? And so the fact that both of these compositions on the Tate module are automorphism shows that the induced morphism F and its dual morphism on the Tate modules is injective and surjective separately. One composition shows that that F is injective and the other shows surjective. I'll leave that as an exercise for you to work out. It's easy. Okay. Now I actually claim that these L-adic Tate modules are Q isomorphic. So we could just check that by checking that these isomorphisms we've produced are Galois equivariant, but that's easy. The Galois equivariance just follows from the fact that F itself is defined over Q. Okay. So look, so what did I just prove? I just proved that if you give me a Q isogeny F between two elliptic curves E and E prime over Q, that their L-adic Tate modules are Q isomorphic, as long as L is a prime that doesn't divide the degree of the isogeny. So for almost all primes, L. But then you can use Neuron-Og-Shafarevich, right, to see that E prime has good reduction at V if and only if E does, you see? Because you can use one if and only if 4, basically. You have isomorphic L-adic Tate modules for some primes L not equal to the characteristic. Okay, so those Tate modules will be unramified at the same place as V. And so the two elliptic curves will have the same places of good reduction. Okay, so what does this show? This shows that E and E prime have the same primes of good reduction and hence the same primes of bad reduction. Okay. And then by functoriality and basic properties of neuron models, a Q isogeny from E to E prime descends to an FP isogeny from the reduction of E mod P, which we'll call E tilde P, to the reduction of E prime mod P, which is written E prime tilde sub P, if P is a prime of good reduction for each curve. You can look on Math Stack Exchange at a thread called The Definition of the Natural Reduction Map for a discussion about this. The discussion above on FQ points, so the discussion involving Tate's isogeny theorem and the slide prior to that, then shows that AP of E equals AP of E prime whenever P is a prime of good reduction for both curves. Okay. And then recall from the first video on elliptic curves that an elliptic curve E over Q has bad reduction at a prime P if and only if P divides its minimal discriminant. And so what this shows is that AP of E equals AP of E prime for at least all but finitely many primes P. Okay. So good. So we have AP of E matching AP of E prime, if E and E prime are elliptic curves over Q, which are Q isogenous, whenever P is a prime of good reduction for each curve. And those primes of good reduction are the same for each curve. That's what we've learned so far. And this kind of uses an amalgamation of material covered on previous slides in this very video. Okay, but that's not enough. So why, for example, do E and E prime have the same primes of multiplicative reduction? So this is as far as I can tell, this requires a little bit more high-powered thinking. So you can use Grothendieck's inertial criterion, which is some sort of generalization of Neuron-Ogg-Shafarevich. If you want a proof of this criterion, you can see Liebke's semi-stable reduction of curves followed by Conrad's semi-stable reduction for abelian varieties, or you can go OG and just look at SGA7. We'll be discussing this result a little in chapter 17 of my notes ourselves. Okay. Anyway, what does this criterion say? It says that E over Q has semi-stable reduction at a prime P if and only if the image of inertia at P under the L-adic Galois representation attached to E is unipotent for some, or in fact equivalently for all primes L that aren't equal to P. So unipotent just means the matrix is, 1, 1, star, 0, like this. Okay. So for all primes L that aren't equal to P and co-prime to N, we know rho EL is isomorphic to rho E prime L, because remember, the L-adic tape modules for these primes are isomorphic as Galois modules. We just got done talking about that. Okay, and these representations are on the L-adic tape modules. And so I can conclude that E and E prime have the same primes of multiplicative reduction because they have the same primes of good reduction, and by Grothendieck's inertial criterion, they have the same primes of semi-stable reduction. And so they must have the same primes of multiplicative reduction as well. Okay, but if they have the same primes of good and multiplicative reduction, then they must have the same primes of additive reduction as well. Okay, we're almost done. So why do E and E prime have the same primes of, for example, split and non-split multiplicative reduction? That's easy to see. So you can use properties of the neuron model again. You can descend your map F to an FP isogeny between the neuron models of the reduced curves. But this map very clearly sends, a node, if it exists, to a node. And then FP tangent lines will clearly map to FP tangent lines because it's an FP isogeny, for goodness sake. Okay, and then for the same reason, non-FP tangent lines will clearly map to non-FP tangent lines. And so split and non-split multiplicative reduction types are preserved by Q isogeny if you have two elliptic curves over Q. Okay, so if you just look at the formulas for the local L functions, you see that E and E prime have the same global L functions. Okay, so I would see my previous video on L functions. I think that's 1, 2, or 3 videos ago, I'm not sure. Okay, and this is because they have the same primes of each reduction type, and the local L function, the local L factors are determined by which reduction type the prime has. Okay, and then because E and E prime have the same AP values, the local L factors at primes of good reduction are the same, and so you're all set. If you want to see a proof of Neuron-Ogg-Shafarevich, I would just see Silverman 1. Okay, now as amazing as that was, so what's the upshot? Again, the upshot is two elliptic curves over the rationals that are Q isogenous have the same L functions. And as amazing as that is, it turns out the converse is true. And this is Falting's isogeny theorem. Two elliptic curves E over Q and E prime over Q are Q isogenous if and only if AP of E equals AP of E prime for all, or in fact for all but finitely many, or in fact for all but a set of density 0 primes P. And moreover, this happens if and only if the L functions of E and E prime match. Okay, so for a proof of all of Falting's finiteness theorems, you can see Falting's original work, finiteness theorems for abelian varieties over number fields. But then I wouldn't start there. I would start with Darman's rational points on curves and the book Arithmetic Geometry for a more in-depth exposition of Falting's theorems. Okay. Falting's is known for, among other things, his proof of the Mordell conjecture, now known as Falting's theorem, which says that if C over K is a curve of genus G at least G bigger than 1, then C of K, the number of K points on C, is finite for any number field K. And to prove that theorem, you have to use this isogeny theorem at some point. So Falting's also proves that. Okay, so we'll be talking about Falting's theorems in more detail in chapter 18 of my notes. Okay, perfect. So next video, we'll be looking at a little bit of Eichler-Shimura theory, but we will be using that theory to show that the converse to the modularity theorem holds, okay? And then we'll start pushing our way towards actual modularity. So I'll see you then. Thanks for watching.